Okay, ladies and gentlemen, let's continue with chapter 7 on external forced convection. Forced or convection consists out of a few chapters. In the previous chapter, in chapter 6, we've looked at the fundamentals. In this chapter, in chapter 7, we look at external forced convection. External tells us it is convection on the outside of bodies. The next chapter, chapter 8, would be internal forced convection. So that would be forced convection, heat transfer inside heat exchangers, tubes, etc. And then the last chapter, chapter 9, would be natural convection. With this chapter, chapter 7 of Sengel and Kejar, we've already completed 7.1, which is the drag and heat transfer in external flow, and also parallel flow over flat plates. When we did the work, there were a lot of fluid mechanics in it, and I hope by now you can see that there's a very good correlation between the fluid mechanics and the heat transfer, and you cannot really disconnect it from each other. So I did a lot of trouble to show you all the fluid mechanics equations together with the heat transfer ones so that you can see how everything fits together. Now, with the last lecture, when we've looked at paragraph 7.2, the parallel flow on flat plates, we did all the equations of the local Nusselt numbers, the average Nusselt numbers for laminar flow, for turbulent flow, and cases where on a flat plate you have laminar flow and turbulent flow. So you end up with a lot of equations, and there were many of you who afterwards were very worried about all these equations, when you should use it and the application of it. Okay. But don't be worried, you're going to see, I'm going to do an example now that's going to make it very clear to you. But before we do the example, one of the last things that we also did is we've looked at Prandtl numbers of liquid metals, which have a very, very small Prandtl numbers, and for that there was also an equation. And I started warning you that with all these equations, which is very, very important, is the fine print that goes with the equation. So it's very important that you know where all the work comes from, where it fits in, and what are the limitations of all the equations. Okay. Now, together with the introduction of the cases where we have Prandtl numbers or very small Prandtl numbers, I've told you there's an equation of Churchill and Ozoe, which is equation 7.26, which takes into consideration all the different Prandtl numbers. And then we've also looked at the cases where you have a flat plate and there's a certain part that hasn't been heated. Now, the last part that I want to say on this work, and which is very important, and it is not very prominent in the material, but it will also become more prominent in the next chapter, is that we always have to be very, very careful to distinguish between applications where we have a constant heat flux and where we have a constant wall temperature. Okay, so let's just look at, let's suppose, the case where we have a uniform heat flux. Okay, in comparison with a uniform temperature. A uniform heat flux in comparison with a uniform temperature. Okay, with a uniform heat flux, it would mean that the plate would be heated everywhere. In every meter there will be the same heat transfer. So if the heat flux is 1 kilowatt per square meter, then for every meter we know 1 kilowatt of heat would go into the plate or the aeroplane wing or whatever the body is, it doesn't matter. Okay. In this case, the application might be that the surface temperature remains constant. And the result of that in terms of the Nusselt numbers are quite significant, and so it's very, very important to distinguish between these two cases. So if we have a graph of temperature against X, okay, for both cases, okay, Then, for this case, the temperature of the flat plate would be a constant, Ts. Okay? While, in this case, it might not be it. The temperature might do something like that. So the temperature of the wall doesn't stay constant. Obviously, if we now also want to plot on the same graph the heat flux, okay, then for this case it would be a constant, okay, Q. Okay. And if we also want to plot it here, then it is going to do maybe something like that. This is just schematic in terms of the principle. Okay. Now, if you go and look very carefully at the literature and you look in laminar flow, in comparison with turbulent flow. Okay. If the flow is laminar, then the Nusselt numbers, if we would compare these two cases, okay, if we would look at the two Nusselt numbers and we would do the comparison, then there will be about 40% typically, and even in some cases more, difference in the Nusselt numbers. Okay. So the Nusselt numbers would vary by very easily 40% and more. In the turbulent flow cases, if we look at the Nusselt numbers, let's call them 3 and 4, and there might be many correlations that you can use. If you would now go and compare them, then the errors or the differences would be about 4% and even less. Okay, now in between we obviously also have the transition flow regime. Not a lot of work has been done in that regard, and not a lot of work has been documented in your textbook. Some has been documented by Kajar and Tom, but we are not going to focus on that. The principle, however, is that with many of the equations, when you look for the Nusselt numbers, if you design something, okay, and you need to get the Nusselt number, and then you will need to get a correlation, or you will need to get it from tables. The first thing is when you start seeing it, we already start seeing the equations, the first thing you have to go and ask yourself, where and when can I use these equations? Okay, so you have to determine, is the flow laminar or turbulent? If it's laminar, then you must see red flags. Very, very important. Is my application an application where I have a constant heat flux, or is my application where I have a constant wall temperature? So immediately you have to distinguish between the two different Nusselt numbers, and you have to go and get the right Nusselt number. So a lot of work, or if you do design work and you have a convection heat transfer problem, the most important thing is always to distinguish and to go and read the fine print and to make sure when and where you can use the Nusselt number and when is it valid and not. So please be very careful for that. And for this reason, you will see that the moment when the flow is turbulent, that people will not even normally say it is for a constant wall temperature or a constant heat flux, because it really doesn't matter. And most correlations in literature, if they are good, the heat transfer coefficients would be plus or minus 20%. Okay, so they are not that accurate in any case. So a 4% on that is not going to be a big deal. Okay, but in the laminar flow regime, it is very, very important. And we will see applications of that also in the next chapter. Let's do an example. And it is an example which is based on example 7.1 in the textbook of Sengel and Gajar, but I'm going to take it apart. Okay, so we are going to look at this problem from many different sides, but let's just start with it as it has been given. It is the case where we have oil at 60 degrees Celsius and a velocity of 2 meters per second. Oil, and it flows over a flat plate with length 5 meters. 5 meters, and its surface temperature is 20 degrees Celsius. Okay. And the width of the plate in the Z direction is 1 meter, which means that the surface area of the plate is 5 square meters. Okay. And the question is, determine the drag on the flat plate and the heat transfer. Right, before we do that, let's just look at the film temperature. The film temperature is the average of the surface temperature and the free stream temperature divided by 2, and that is 40 degrees Celsius. Okay. So at the temperature of 40 degrees Celsius for oil, we have to go and get the properties. So the properties in the tables, in the textbook, we have to go and select it at the temperature of 40 degrees Celsius. So that is the standard, or the norm that has been used in most of these equations, and it makes things just so much easier. Okay, so that is the temperature, and at that temperature you can now go and get the density of the oil, which is 876 kilograms per cubic meter. The thermal conductivity is equal to 0.1444 watts per meter Kelvin. Okay, the Prandtl number is very high, 2962, and the kinematic viscosity is equal to 2.485 multiplied by 10 to the minus 4 square meter per second. Okay, so that's the properties. You go and get it from your textbook, but very importantly at a temperature of 40 degrees Celsius at the film temperature. Are you all happy with that? Any questions? Nothing? Am I going too fast, or are you with me? Everything fine? Right. Okay. There's no recipe to be followed. Okay, but if you look at the literature in terms of what we've done, one of the most important things when we look at a flat plate is to determine if the flow is laminar or turbulent. Okay, and to do that we need the Reynolds number. So the Reynolds number is sort of the most obvious thing that we have to go and calculate, and we're going to calculate it based on the length of the flat plate. The Reynolds number based on the length, because that is, in terms of the equations, that is given that you need to determine it on the length. Okay, or we can write it as the velocity multiplied by length divided by the kinematic viscosity, where the kinematic viscosity is equal to the viscosity divided by the density, so that value there. Okay. Now, because this is so elementary, I'm going to ask you to please forgive me. I'm not going to put in all the values. Okay. The velocity is equal to 2. The length of the plate is 5. The kinematic viscosity is that. No? Okay, so the only thing that is sort of an important issue at this stage is the length, and I'm going to come back to the length later on. So the length we take as 5 meters, and if you go and calculate the Reynolds number, then it is equal to 40,241. Okay, and that is smaller than 500,000. So it means we have laminar flow. Just laminar flow. So if I just draw it schematically, okay, for the 5 meters, if I just draw it schematically, there is the boundary layer as it increases, And in the 5 meters, there's no transition to turbulent flow. Everything is laminar. Do you agree? Okay. So, once you've made this conclusion, it's very easy. If you look at the equations that we've looked at with the previous lecture, you can go and look for the equations for laminar flow. Okay. And they are, so laminar flow, firstly, and we want the average ones. Okay. The laminar equations and the average ones, and then the average friction coefficient would be equal to 1.33. Reynolds, based on the length, to minus 0.5. Okay. And again, the Reynolds number, there it is, so I'm not going to do all the substitution. You can go and do it at home. But the result would be a CF value of 0.00663. You happy with me? Happy? Okay. Now the drag. Okay. We want to calculate the drag. The drag is equal to CF multiplied by the area, rho V squared divided by 2. Everything elementary. Okay, the CF, friction coefficient, we've just determined it. The area is 5 square meters. 5 meters of plate, 1 meter in width. Okay. The density is 867. The velocity is 2 meters per second. You can do the calculation, and the result would be that the drag would be 58.1 newtons. Okay? Yep.
So I just want to check that area, it's just the top surface.
Yes, yeah, just the top surface. No, not the bottom, just the top. Okay, just the top. Okay. Okay, so yes, that is just for the top, because we want to know on the top what the heat transfer is and what the drag on the top surface is. Okay. Right, now we need to get the Nusselt number. And again, it would be the Nusselt number for laminar flow and for average. We want to know the average heat transfer coefficient over the plate. We do not want it at one specific point. We want to know the average. Okay. So then the Nusselt number is equal to 0.664 multiplied by the Reynolds to the 0.5 multiplied by Prandtl to the third. Okay. Again, everything elementary. We've got the Reynolds number. The Prandtl number is 2962. Just do the calculation, and the result is a Nusselt number of 1913. Okay. The Nusselt number is equal to the heat transfer coefficient multiplied by a characteristic length divided by K. It's equal to 1913. Okay. 1913. Now we want to get the heat transfer coefficient based on the length of the plate. Okay. Because that is what that Nusselt number was derived for in terms of the length of the plate. Okay. So that is a known. We've got the thermal conductivity is 0.1444. It's equal to 1913, and we can solve the heat transfer coefficient as 55.25 watts per meter square Kelvin or degree Celsius, whichever you prefer. Okay, any questions? Yep.
So I just want to check, how does it apply to the Prandtl number being outside the 0.6260? Is this still valid there, or I'm not sure?
Yes, the equation is valid for Prandtl numbers larger than 0.6 and smaller than a very large number. I can't get the value quite now, but it is in range, I'm quite sure. Okay. So obviously, if the Prandtl number is not in range of your equation, you need to go and get the equation. Okay. But just remember, the equations in the textbook are some of the most important ones. It's not all of them. Okay. Otherwise, the textbook would be that thick if you would like to include everything. Okay. So that is the heat transfer coefficient, and now we can go and calculate the heat transfer rate. is equal to the heat transfer coefficient multiplied by the area multiplied by the temperature difference. Okay. In this case, the heat transfer would be from the oil to the plate, okay, because the oil is at 60 degrees Celsius, and that would be the heat transfer rate. Okay. We've got the heat transfer coefficient, 55.25. The surface area is 5, and the temperature difference is equal to 60 minus 20, and then we can calculate it as 11,049 watts. Okay. Please do not write me an answer like that in the test and exam. That is 11 kilowatts. Okay. Okay. Are you happy with this first very simple part? Okay. Right, let's change the problem. What if the plate was 1,000 meters in length? Okay. So let's make it long now. Okay. So now the plate is 1,000 meters. Okay. Same conditions. Temperature is still 20, the oil at 60, velocity, everything. It's just the length that is changing. And obviously the surface area now changes to 1,000. Because it's 1,000 meters multiplied by the width, which is 1 meter. So it is 1,000 square meters. Okay? So what question would you like to ask now if I would give you this problem?
Critical length.
What is the?
Critical length.
Yeah. What is the critical length? Because if we know that, then we know where the flow would change from laminar to turbulent. So let's calculate that. So the critical Reynolds number would be equal to the velocity multiplied by, let's call it x critical, divided by the kinematic viscosity. Okay. That would be 500,000. Okay. It's equal to the velocity, which is 2, multiplied by x critical divided by the kinematic viscosity, 2.485 multiplied by 10 to the minus 4, and it gives us a critical length of 62 meters. 62.13, something like that. Right, now that we know that, and that is a very important thing to know, if we look at this plate of 1,000 meters, okay, if that is 1,000 meters, that is about a tenth of it, so that's about 100 meters. So on scale, it would mean that transition typically would occur there. So that is laminar flow up to there, up to 62 meters, and after that, the flow would be turbulent. Okay, so now that you know that, which equations would you use? What would you do as an engineer? Okay, so if you are as lazy as I am, you would look at this problem and say, you know, can't really contribute that much, you know. I'm going to assume it's all turbulent. Okay, so let's make that assumption. Okay. Okay. Assume all turbulent. So my judgment is that in general the flow is turbulent and the laminar region would be negligible. Okay. So if we go to the turbulent case, then these equations are not the same. Previously this was for laminar flow, now we need it for turbulent flow. Okay, again the average ones. And then for turbulent flow the equation looks like this, 0.074 divided by Reynolds number based on the length divided by a fifth. Okay, so it's very easy now, isn't it? I mean 0.074 divided by 500,000. You happy? Right. You're awake. That is not, this Reynolds number is the Reynolds number based on the total length. Okay. The critical Reynolds number is the Reynolds number at that position there. Okay, at 62 meters. Okay. So we also need to determine the Reynolds number at 1,000 meters, which would then be equal to the velocity L divided by the kinematic viscosity, and now L is 1,000. Okay, L is 1,000 now. We want to know what is the Reynolds number based on the length of the plate. And if you do that, it is equal to 8 million. Okay, 8 million. And it is just smaller than the boundary condition up to 10 to the 7. So it is valid. Okay. So this equation now, we have to use this value in there. Okay. And then we calculate the friction coefficient. And the result of that is that it would be equal to 0.003077. And then determine the drag, which is equal to CF multiplied by the area, rho V squared divided by 2. The friction coefficient is equal to 0.003077. The area now is 1,000, of course, okay, because we've got 1,000 meters multiplied by 1. We've got the density, we've got the velocity, we can calculate the drag, and the drag would be equal to 5390 Newton. Okay. And if we look at the problem in the previous case, the drag was about 58. Okay. Now it is 5.4 kilonewtons, so we can at least see it is more and it is not less. Okay. Right. Then we also now have to get the Nusselt number. And the Nusselt number for turbulent flow. So it is 0.037 divided by the Reynolds number, 0.8, Prandtl to the third. Okay. And the result is a Nusselt number of 177,811. Calculate the Nusselt number, the heat transfer coefficient multiplied by L divided by K is now equal to 177,811. Now the length is 1,000 meters, because it is the Nusselt number based on 1,000 meters. The heat transfer coefficient would then be equal to 25.68 watts per square meter degree Celsius. Okay, 25. So we can see that the average heat transfer coefficient is actually now lower than previously. Previously it was 55, now it is lower. The heat transfer rate is equal to the heat transfer coefficient multiplied by the area multiplied by the temperature difference. Heat transfer coefficient is 25.68. The area is 1,000. Temperature 60 and 20. Do the calculation, and then the heat transfer rate would be 1 megawatt. Okay, 1 million watts. Okay. Now there are always people who's a little bit too critical and would say, no, wait a minute, you know, this assumption of you, the shortcut that you've made, I don't know. I'm not so sure. Well, let's go and check it. Okay. So what we're now going to do is take into consideration the laminar part. Okay. So if we look at this plate now, which has a laminar part and a turbulent part, we need to get the Nusselt number where we've done the integration of the laminar part and the turbulent part over the lengths. Okay? And that equation, firstly in terms of CF, the drag, has two components. The laminar part, 0.074, divided by the Reynolds L to the fifth, minus 1742 divided by the Reynolds L. So that is how the friction coefficient looks like. And the result is, again, we've got everything. The Reynolds number is still the Reynolds number based on the total length. That is how it has been derived. Okay? If you go and calculate the friction coefficient, it is equal to 0.00286. And then the drag, which would then be equal to 5011 newtons, okay, which is equal to 5 kilonewtons, and in the previous case it was 5.4 kilonewtons. Okay. So we can see there's a small difference, but it is small, it's not big. And then the Nusselt number, the laminar part, is equal to 0.037 multiplied by Reynolds to the 0.8 minus 871 multiplied by Prandtl to the third. Okay. If we calculate the Nusselt number, it is equal to 165,303. Previously it was 177,000, so there's a little bit of a difference. The heat transfer coefficient would be equal to 23.87 watts per square meter degree Celsius, and the heat transfer rate when we calculate it is 0.96 megawatts, which for all practical purposes is still 1 megawatt. Okay? Right, so the question that many of you would like to ask me now is, well, if I'm in the test or exam, you know, when must I use this approach, or when can I use that one? I do not have an answer. It is an engineering judgment. You have to look at the problem and decide yourself. Okay, so I myself would have used the turbulent approach only, okay, because I would say, well, this is less than 10%. But again, it depends on what I'm busy with. If I would like to get first order of magnitude types of answers, then that would be more than valid. But if I'm developing a product, I'm trying to compete against others, you know, then obviously need to take it into consideration, because maybe this might be a very important difference for the client from 1 megawatt to 0.96 megawatt. Might be a very important difference at the end. Now let's again look at this problem, but what I'm now going to do is let's change the length so that the total length of the plate is 130 meters. So 130 meters. Again, the width is 1 meter, so the area of the plate is 130 square meters. Okay. The boundary conditions are exactly the same. The oil at 60 degrees Celsius, velocity 2 meters per second, surface temperature 20 degrees Celsius. Okay? Right. Now, we've already calculated that the critical length is 62 meters. Okay? Which means that the turbulent part should be 68. So approximately, if we plot this thing according to scale, This part, the first 62 meters, we're going to have laminar flow, and the next 68 meters, we're going to have turbulent flow. You agree? So, if you have this case, I think you would agree to me that I think it would be a far stretch if you say, well, I'm just going to use the turbulent approach, okay? Because it's very balanced, okay? So, again, let's do this one. Calculate the Reynolds number based on the length of the plate. Again, be the velocity multiplied by L divided by the kinematic viscosity. Now, the length must be equal to 130 meters. Okay. The total length of the plate, 130 meters. And the result of that would be that the Reynolds number is 1 million. Okay, it's not surprisingly, it should be larger than 500,000. Okay, it's turbulent. The total, based on the total Reynolds number. Right, now, if we want to calculate the friction coefficient, in this case, it's very clear we have to take into consideration the laminar part also. So it consists out of the laminar part, 0.074, divided by the Reynolds to the fifth, minus 1742, divided by Reynolds based on the length. Okay. I'm not going to give you the friction coefficient, but jump to the drag. The drag, if we calculate the drag, which is then equal to rho CF multiplied by the area, rho V squared divided by 2, then the drag would be equal to 675 newtons. Okay. With the Nusselt number, we have to take into consideration again the laminar part and the turbulent part. So the laminar part is 0.037, Reynolds to the L 0.8 minus 871 multiplied by Prandtl to the third. Yep.
So yesterday when you used that formula, you said it's only valid for half a number between 0.6 and 60.
Between that and 60. I will just have to go and check. Okay, so I will let you know with the next lecture. Okay. Right, so the Nusselt number in terms of the laminar part and the turbulent part. And if we now go and calculate the Nusselt number and the heat transfer coefficient would be 24.72 watts per square meter degrees Celsius. And if we calculate the total heat transfer rate, it would be 129 kilowatts. Okay, 129 kilowatts now on a 130 meter plate. Right. Now, that's not the end. The question would now be, if you look at this critically, is to ask that in the laminar part, how much heat transfer would be in the laminar part and how much would be in the turbulent part? Just to give us an idea of the heat transfer rates. So let's go and calculate. So let's first go and calculate what is the heat transfer rate in the laminar part. Okay, so that would be over the first 63 meters. Okay. So now we have to go and calculate the Reynolds number, VL divided by the kinematic viscosity. L now, the length now would be 63 meters. Okay. It would give us a Reynolds number of 498,994. If you calculate it, if you use the exact value of 62.13, it would be exactly 500,000. So that's the only reason why it is not that. Okay. Okay, so some of my values I've thrown away, but it should be 500,000. Okay, so for 500,000, it's laminar flow, then CF is equal to 1.33, Reynolds to the minus 5. From that, we can calculate the drag as 205 newtons. Okay, 205. Calculate the Nusselt number, 0.664, Reynolds to the 0.5, Reynolds to the third, and that is, the Nusselt number would then be equal to 6736. Calculate the heat transfer coefficient, it would be equal to 15.69 watts per square meter degree Celsius. And then the heat transfer rate would be equal to 38.91 kilowatts. Okay, so, yep, question?
So that length, should that be 62 meters?
Yeah, 62 point something. So I've just assumed about 63 meters. I can't remember, did I say 62 previously? Where is it? Oh, 62. Yeah, sorry. Okay. So it should be, 62 meters. Okay. So it should be 62 meters. I think it is actually 62.13 or something like that, but in any case, if you also use that correct value, then you should get a Reynolds number of exactly 500,000. Okay. Right, so let's just look at this plate now again of the first part laminar and the second part turbulent. The first 62 meters and then the other 68 meters. Okay? So in terms of the drag for the first 62 meters is 205 newtons. Okay. For the total length, it was 675. So this part is 675 minus 205. So it's 470 newtons, is that right? So the contribution of to the drag in the laminar flow is 205. In the turbulent part, it's 470. And with the heat transfer, this part would be 39 kilowatts, and this part would be 90 kilowatts. So just orders of magnitude, we can see that the contribution of the laminar part is about 30% and the turbulent part 70%. Okay, you all follow the problem? Okay. In terms of, somebody asked me now, in terms of the validity of the Reynolds number, that maybe this equation is not valid. I will go and check. We're going to have many cases where you will have to do calculations where maybe you're on the border with a Prandtl number or a Reynolds number. Just for the academic exercise, you know, we will go through it. The right thing would be to go to literature and to go and get a better equation. Many of the equations also in the textbook are the simpler versions. Okay. Because otherwise it just takes a long time to do all the calculations. So in many cases there are more accurate equations available, but much longer and more complicated to calculate. Okay, I think that no, I still have 5 minutes and I can still finish paragraph 7.3. Okay. Paragraph 7.3 is about flow around cylinders and spheres. Cylinders and spheres. Okay. Now just coming back to your fluid mechanics, just think of an object like a cylinder and a sphere. In fluid mechanics, they are considered as blunt objects. Okay. So if you have flow around a cylinder, then we would like it to be like that. And that is exactly what happened if the Reynolds number is very, very low. Okay. As the Reynolds number actually increases, we have separation that occurs at the back. And the separation, these vortices are exactly symmetrical. Okay. If we increase the Reynolds number even more, then unfortunately things are not symmetrical anymore. One of these bubbles will break away before the other one, and it would make the flow very unstable at the back. So we will see that we have flow separation, vortices. Okay. And now because of this, the pressures on this side and that side are not the same anymore, and that causes lift. So if you would go and look at telephone lines with wind, okay, from the side, after a while it would start going up and down. It is because of the lift forces which is being generated by the separation of the vortices at the back. So let me show you a video quickly. Okay. Okay, if we can get it to work, there it goes. Okay, so this is typically what happens with a flow. Let me just do it again. There we can see it's quite symmetrical, and then at the stage the Reynolds number increases, then at the back you can see how the flow starts doing that. Not symmetrical anymore. Okay, and the flow vortices there at the back. Okay. Now there are many videos on YouTube that you can go and look at. I've just selected 3, all of them saying the same thing, but just differently. See the vortices, how there they go. Okay. Okay. We'll show it again. Okay. Go. Starts are very symmetrical, and then we have becomes unstable. So there we can see the Reynolds number 500 now. I think it started with 5. Okay, and here's a third one. Okay, this one that I like is the particles that is being released at the front, and as you can see how things change at the back. Okay. Very chaotic in terms of following the particles that started at the beginning all at the same time over a very symmetrical object. Okay. Okay. So just 10 seconds. What I want to say is if you now go and measure the drag as a function of Reynolds number, we get something like that. Okay. So this is the moment when the vortices start forming. You get a very complicated graph like that, and we will discuss it again with the next lecture. Ladies and gentlemen, I think it's the last. No, still see you tomorrow. That's right. What is it? Is it Friday today? No, Thursday. Oh, right. There's no lecture tomorrow. That's right. Okay. So enjoy your holiday. Thanks, Erin. You can cut.